Does oxygen occur as O's? So it's not made from the element on this planet in its in its standard state. So you have to watch those subscripts. You have to know what's going on with the reaction. This could potentially be something that the College Board would throw out there on the test, or maybe even me. I could give you all four and say, which one of these is the standard heat of formation for, and I could have, you know, either a particular compound or just for the product. All right, so let's take a look at number A. Number A. I don't have enthalpies of any reaction. All I have is enthalpies of formation. Okay? Well, you probably, and if you had Mrs. Stone, I did find out this morning, you talked about enthalpies of formation because you got that chart and all that kind of stuff. And you probably memorized a reaction. It was like products, is it what? I don't have it memorized because I don't measure reactions. Okay, so I'm going to ask you right now, why the heck do I need to memorize products minus reactants? And all of you are going to say, you don't, Geyer. In fact, you know what? We don't ever need to memorize this reaction. Thank you, Josh. Thank you. Bump, man. All right, here's what we're going to do. So let's take a look at sodium hydroxide. Number A. All right, so we'll do this. Number A. There we go. Got to annoy somebody today. So let's find sodium. Oh, look at sodium hydroxide has a heat of formation of negative 426.7. That means if 1 mole of that is made, 426.7 kilojoules per mole are given off. Is it being made? Oh, it's being used, right? So you know what? I'm going to put this up here with a plus sign. Plus 426.7.
Oh, you don't need to memorize it.
Yeah, you see how it works now? You see, I don't need to memorize it. The problem with memorizing is you can sometimes get it wrong. If I think my way through it, I'm not going to get it wrong. So let's go to HCl. HCl gas. Let's find, oh, there we go, top of the second column. If 1 mole of that is made from constituent elements, it gives off 92.3 kilojoules per mole. But I'm not making 1 mole of this, I'm using 1 mole. So you know what? I'm going to change the sign. All right. Now, sodium chloride. And by the way, I guess we should check to make sure the equation is balanced. Is it balanced? Na, Na, OH, OH, and H, and H. Okay, so it's balanced. All right. Sodium chloride, solid. NaCl. Where the heck is the NaCl stuff? The NaCl. Oh, there we go. Third one down in the left-hand column. If 1 mole is made, it will give off 411.0 kilojoules per mole. Well, look at this. I'm making 1 mole of this. So I'm going to put it up there just as it's written, minus 411.0 kilojoules. Now, I'm going to do one thing, because I've been writing stuff I don't need to write right now. Does this reaction have only 1 product? No. And it's just asking for the enthalpy of the reaction. So what am I going to start getting? Oh, I didn't do it actually. What am I going to get rid of now? I'm going to get rid of these because they're not going to end up in my answer because I'm not making only 1 thing and 1 mole of that 1 thing. So I'm just looking for how many kilojoules does this reaction give off or take in. So I'm just going to get rid of it now because I don't want to write that stuff. I don't have to. All right, H2O gas. Where is H2O? Oh, there's H2O gas. Right-hand column, second one down. Am I making that stuff?
Yeah.
All right, so I'm going to put it down with the exact sign that it's got. And then minus 241.8. Now, if there were 2 waters there, I would need to look at the fact that it's making water gas, not, say, water liquid or something like that. So do you see why I don't want you to memorize the equation? If I understand bonds making and bonds breaking energy in, bonds breaking out, if I understand the definition of heat of formation, you're making 1 mole. Whatever is on this paper, that's for making 1 mole. Well, if I'm going to move it to the other side of the arrow, just change the sign. Now I don't have to memorize anything. I can't ever get this wrong unless I fat finger my calculator. All I have to do is combine these terms. Yeah. All I have to do is combine those terms and I'm going to have the heat of reaction. So Since I already did that, let's see what you all get. Huh?
I don't know if I can do it.
Oh,
I don't know if my brain doesn't hurt.
well, you're done thinking. Now? You know, I've had math teachers say, don't plug and chug. Well, why can I not plug and chug? I've done all the thinking. What do I have to do now? Just type on a calculator. There's no thinking that has to go on now. I've already done all the thinking. So I like that plug and chug. Stick the numbers in and
Hey Amani, if you're plugging and chugging along with us.
well, in that particular case, they might ask, you know, show me which equation is correct. Because the College Board could do that, and then you'd be looking for positives for the things on the reactant side and negatives for the things on the product side. It's a good question, Natalie. Did you get negative 165.4 kilojoules?
Wait.
I did.
Yeah, it's good because that'd be the wrong answer.
I knew you were gonna.
I was just wondering what was up with you.
Negative 133.8 kilojoules. Yeah.
Oh, that was so close to part B, so I just thought you were asking about part B. I thought he said 565.
All right, so let me pause. I'm going to give you time to work on some of these.
Yeah.
Here's what we've got so far. So in this unit, we have talked about internal energy and how that's heat and work together. And then chemists decided, let's forget the work part, because in many cases we can. So we defined enthalpy. We talked about how I can go into the lab and measure enthalpy if I have an open calorimeter. And if I pay someone a lot of money, they can use a bomb calorimeter to get internal energy. So that's the best thing. Measure it exactly. If I can't measure it, well, hey, maybe I can look it up. Maybe someone else has measured it and I can get the heat of the reaction and calculate it. Oh, they don't have my reaction. Well, you know what? Maybe I can get the heats of other reactions and combine them in such a way that I can get the heat of the reaction. Hess's law. Okay. What if I don't have heats of reaction? Well, I might have enthalpies of formation. And still, because of Hess's law, because enthalpies are additive, I can still add these things together and get the heat of the reaction. So this is just as good as enthalpies of reaction. It's not as good necessarily as measuring it, but if someone else has already done the work, hey, why not? The thing we're going to talk about next is going to be the less good thing. So anything after this point is going to be not so good. So what we begin to talk about on Monday will be approximations. So today is the end of this is really good and legitimate.
I just have a random question.
What?
For this one first, so is there any
I don't want you stole my calculator.
Oh, never mind. There's.
There you go.
I'm-
Yeah, I had to add it. How you doing? I'm good. You know, before you leave at the end of this year, you need to sign that. Just put a little signature on there, and then I can get it laminated.
Okay.
Okay, we'll have to do it before you're gone because they tend to screw the lamination up downstairs.
Gotcha.
You know, one out of every one thing gets screwed up in some way, shape, or form.
Cool.
Yeah.
I mean, not cool.
Yeah, I know. It's kind of funny. Yeah.
Oh, geez, Rick. You don't like Rick and Morty? I just always say, oh, geez.
But most of my
Oh, geez.
Christian culture people that I know are down there, so I wanted to ask you because they're not there. If
Negative 113.
If you share something with them, wow. Tell us we just got it last week.
That's wrong.
Partners use that, so it's going to be great. I think 113.0.
yeah, so it's not just one thing.
How many?
This is me.
Give me that. So I'm playing give me that again. Give me again. This is. I'm not saying I'm the only one. But I'm saying there's any way that I'm going to put this on the video.
If you do it, best one help me with all of these. AV or bell.
Oxygen.
Right, yeah, so you got email me something.
Yeah, because
Oh, yeah.
I have a question.
Yeah.
So we're like measuring, like we go into a lab and then we use a calorimeter, and then when we're using that open calorimeter, we're essentially measuring just the cube of heat. But when we have a bomb color, we can actually get the internal temperature.
Right. Now here's the thing. If say we're trying to measure the heat of solution for sulfuric acid, and I say that because it gives off a lot of heat. I'm actually changing what I've ever done before. I'm trying to come up with a lab for us to do next week where you can maybe see this, and it wouldn't be a multi-day thing. It'd be one day only, and we wouldn't write a lab report. It'd just be, we would do it. Yeah, no, this would just be, let's do it, and let's take what we've been doing in class and see if we can apply it. Right. So let's say I'm going to dump concentrated sulfuric acid into water to make a diluted solution. What's going to give off a ton of heat? There's no gas generated at all. You'll have a little expansion of the water because it's going to heat up, but you'll not see that. So the amount of air that's pushed out of the way is so small that it just really doesn't matter. We're going to forget it. So assuming you do the best job you possibly can in the lab and you get a perfect delta T, and assuming, because all college labs will say we have to figure out what the styrofoam cup calorimeter's C value is, well, I would argue, you know what, that's a waste of half a bell that we don't need to do. So we're going to have a little error there. But if you were to take your value and we were to look in a table to find out what it really should be, your percent error probably is going to be really, really, really tiny. Only because not much work was done and the styrofoam cup calorimeter's C value doesn't need to really be calculated. Okay? So that's why chemists have said, in most cases, let's just forget the whole work thing. Yeah, I mean, because it is so tiny compared to the amount of heat given off that we really don't care. All right, and everything we're doing is model-based anyway, and all of our models have flaws in them. So there's a lot. This year we will do a lot of. There's a term I made up called negligibly. Right, and it showed up on the back of one of the shirts. I think the purple one over there next to the cabinet, because someone made the comment that I'll negligiblate your grade. Okay, but so we're gonna consider certain things to be negligible because compared to everything else, it just doesn't matter. It's so small that we can forget about it, and we'll do that in a lot of things this year. And it's not just because I'm trying to oversimplify things. That's just what chemists do. So if you really need the real value, like case in point, ideal gas law. If gases matter to you, you won't use the ideal gas law. You use the real gas law. But for almost everybody, the ideal gas law gets you close enough that we don't really care. Okay.
Okay. So let's look at. We were just talking about that lab, that little test one day. Can we have like participation points given?
No. This is AP Chem. No participation points.
Okay.
You'll be fine without them.
Oh gosh darn it. I had like such a good when you have a bomb calorimeter and it's like inside the equation, is it like, do you calculate like the change of heat and pressure of just the water or of the water and the
So
substance?
the Q equation for a bomb calorimeter will have two parts. The part for the water, like we would with the styrofoam cup, but it will also have a part for the bomb itself because it's metal and it will absorb a certain amount of heat. And that C value will be given by the manufacturer of the calorimeter. Or if there were a problem, they would have to tell you what the C value is because you don't know what the calorimeter is made out of. You know, what it's stainless steel, 418 stainless, there's all different kinds of stainless.
But I'm talking about like so like when you're calculating it, okay, that was another question.
Yeah, and there's a slide, if you pull back like early on in the notes, there's a slide that talks about that.
Yeah, I remember. I saw it was like plus.
Yeah.
It was like those two plus each other. But I haven't. Like my question is like second question. Inside the water.
Yeah.
And like how like you have your substance going inside the water. Are you only
in the bomb calorimeter you don't.
In the bomb calorimeter.
In the bomb calorimeter it goes inside the bomb itself because you're going to pressurize it with oxygen to burn it.
Wait, I'm pull up a picture.
Yeah.
Oh, well, this how life was before pictures. I can, or before like internet.
Yeah.
Can't control it.
That's okay. There you go. So the water is all around the bomb. The bomb itself is dry. You put the product in there, or the reactants actually. You put the reactants in there, you'd pressurize it with oxygen, and then you would ignite it, and it would burn, and the calorimeter, the bomb part would heat up, and then it would cool off as the water heats up too. So these two things, the calorimeter itself and the water, would reach a certain temperature.
But how
So-
would it, like if it's in this metal tubeish thing, then oh, I guess it's part of like all of this.
Yeah.
Like it's part of it.
Yeah, and so that's why.
And my mom was like, yeah.
Let's see. There, yeah.
We dropped Amani.
Sorry, Bonnie.
Oh my God! It stopped.